Hello Internet, my name is Quinn and this is Blondihacks. I'm working on the Fleischmann 1950 tin steam toy today, the little restoration side quest that I'm doing, and today we're going to make that little guy a brand spanking new boiler. So let's go. When last we left our little brass boiler, you can see it's been cut into pieces, the poor thing, but I have this nice set of copper that I'm going to use to build a new one. This is all stuff I happen to have in the scrap bins, so that always makes me very happy. Out of curiosity, I measured the thickness of the original, and I was shocked at how thin this brass actually is. It's just 12 thousandths thick. Really remarkably thin. This micrometer, by the way, has a hemispherical anvil on it, so it can be used for measuring thickness on a concave surface like this. Now, the stuff I'm going to be using is 31 thousandths thick, so quite a bit thicker. I'll get this tubing marked out and cut to length next. This stuff is too large for my tubing cutter, so I'm going to use a hacksaw. I'm going to use an old fabricator's trick for cutting a square end on round stock. You wrap a piece of paper around it, and if the edges of the paper line up nicely, then you've guaranteed yourself a square line all the way around the axis of that material. As long as you hacksaw carefully along the edge of your paper, you are good to go. I don't like to do stuff like this on the bandsaw because thin wall tubing is going to be very grabby on the saw, and because it's round, it's going to be very inclined to get grabbed and rolled under, possibly bringing your fingers with it. Make sure to drop it on the floor and ding it up for the artisan flare, and I'll check that that end is reasonably square. The ends are going to be covered, so it doesn't have to be perfect. The original has the flange on the boiler heads on the outside of the tubing, which is interesting. That's actually the opposite of how we would do it traditionally in model engineering. We would typically have the boiler heads inside the tubing because that looks more prototypical. But I want to replicate the look of this original as much as I can. These flanges are also extremely shallow, I'm sure for cost savings once again, so I'm going to try and replicate that detail as well. I'll make sure the tubing is round before I try to make heads for it. Tubing is very rarely actually round. It's usually somewhere around 5 thousandths out of round. I've seen it as bad as 50 or 60 thousandths, as though the factory had shoved a steel egg through it. But this one actually is really, really good. It's within a thousandth. I guess it had a good life. If you need to make it round again, you can turn something the correct diameter, anneal the tube, and hammer that round thing through it to make it round. But I can skip that step and move on to the heads. I've measured the radius of the original heads, and plus the depth of the flange, plus a little bit extra for the radius that will be formed on the flange as it bends over, and I'm approximately marking out that diameter on this piece of copper for the two heads. This copper is the same thickness as the wall of the tubing, because it's easier to silver solder if everything's the same thickness, the same weight of material. I'm also marking out the bend point on the flange, which will be helpful in lining up the hammer forming mandrel that will be coming up shortly. I'll rough cut those out on the bandsaw. It's helpful to have the blanks round when you start the hammer forming because the less excess material there is there, the easier the hammer forming is. But in this case, I don't want to get too close to my line because I'm going to be finishing it up to final dimension after the hammer forming. So I rough cut it on the bandsaw, and then I'll fine tune it a little bit on the belt sander. Again, just trying to get it round and going close to my layout lines, but not touching them to give myself some finishing room at the end. As I said, I am going to be hammer forming these, so I'll need a former and a backer. I found these scraps of aluminum, and conveniently, one of them is already the correct outer diameter, because the tubing is a standard diameter, and I have this aluminum round bar that's the same standard diameter. So I don't have to do any turning on the OD of it to get the right shape, or size rather, for the heads. But I do need to clean up the end and give it a little bit of a radius to create the shape around the flanges that I want. I'll face off the end, as is tradition. You know, I've had some new viewers ask why I say that all the time, and they argue with me that it's not tradition, it's to create a reference face on the... Yeah, I know that. I talked about that in my lathe series. It's a joke. Let's all have a little fun, shall we? Next, I want a little bit of a corner radius on there so that the head that we form with this is going to have a nice bend on it. The original had very, very little corner radius on it, so I'm attempting to, once again, replicate that radius just enough so that the material isn't creased effectively. I measured the radius of the original, and then I copied that onto my blank. Now, yes, this is going to be off by the thickness of the material because I'm comparing inner radius to outer radius, but it's close enough. Next, it's over to the hearth to anneal these pieces for hammer forming. Yellow metals like brass and copper typically come from the factory in a state that's called half-hard, which is essentially work hardened from existing in the world for an amount of time and being manipulated by the steel plant. So if you anneal it up to a glowing reddish orange heat and then let it cool down, it gets very, very soft and easy to hammer form. You can also quench it to cool it down faster. Yellow metals do not harden when quenched like high carbon content steel does. But I don't do that with the first annealing because it will warp it because the sheets are thin and flat. So I put it on the bench and do kind of a plate quench. But once it has a little bit of shape to it, you can start quenching it with each anneal. Once it's cooled down, I can line it up with my hammer form, and I use the inner circle that I had scribed on these pieces. I know you can't see them on camera, but they are still visible to me in person. That allows me to get the hammer form centered on the piece for the initial hammer forming. And away we go. The backer on the other side keeps that area flat while we're forming the flange so it doesn't bow out, and all you do is work your way around. The secret to this process is don't try to do too much at once, just go a little bit at a time. I typically find I can get about 2 laps of the piece and then it's going to need annealing again, because as we're hammering it, we're deforming the material and work hardening it. And copper work hardens quite quickly, so you won't get very far without needing to anneal a second time. And then you can do a little more and then anneal it again. For a piece like this, you probably need 3, maybe 4 annealings. After the first annealing though, it's got that shape to it that is sufficient to align it. So you don't need any kind of alignment pins or through bolts or anything. It will self-align once you've got that first little bit of shape in there. Some more complex pieces, it is helpful to have alignment mechanisms of some sort, but for simple round pieces like this, you really don't need them. Every time I show hammer forming, somebody comments, "Why don't you just stamp them?" And in fact, stamping is how the factory made these. They wouldn't have hammer formed them like this. This is very labor intensive. But my 500-ton press is in the shop along with my EDM machine, so I'm hammer forming. The armchair engineers who tell me to stamp everything seem to be unaware how much force stamping actually requires. Hammer forming copper is really wonderful, honestly. It's a real joy to work with this stuff. When it's annealed, it's so soft, it's like working clay. It really is. You can see how nicely it moves. Now what we're doing here is what sheet metal people call shrinking. We're cramming this metal around a corner and into a radius on 2 dimensions, and that means it has less surface area now than when we started. And what that means is the metal is literally piling up on itself. We're shrinking it into a smaller space. I'll show you the effect of that in a second. But after a few rounds of hammer forming, I got a fit that I was pretty happy with. You want very little or no gap all the way around the mating parts. The more time you spend on joint fitment, the easier silver soldering is, so it's well worth taking your time. Now back to that shrinking thing I mentioned, we can actually measure the effect right here. This material now measures 42 thousandths, so it's actually gotten 11 thousandths thicker, and it's very consistent all the way around the part. It's within a thou of that measurement. You can see the effect of the metal shrinking on the micrometer, which is pretty cool. From a practical standpoint now, though, we actually want to remove that excess metal. This would be mechanically necessary if we were doing a traditional interior head, but for the exterior head, even though the excess material is not hurting anything, it messes up the look of it, so I want to turn down that excess material. Conveniently, the hammer form is now a fixturing mandrel for the lathe and these heads. I'm going to use pressure turning for that. I've got this little pad that I made. It's got emery glued on the back and a center in it that allows me to put pressure on the piece with the tailstock. I have a few of these in my drawer that I've made over the years for different sized pieces. Hopefully that will be enough hold to do the turning that we need. Now I'm going to dial in the copper itself, not the mandrel, because I don't actually care if the flange is concentric with whatever the spinning axis of the copper is. What I care about is removing roughly an even amount of material all the way around. If I try to make it concentric, I might end up making some area too thin. So I want to dial in the surface of the copper, even though it is rough because it's been hammer formed. But, I got it within 5 thousandths, which is pretty good for a hammer formed part. But this will allow me to then just take the 10 thousandths of excess material off that I know is on that flange and hopefully not make any one area too thin. Machining copper is never a good time. It's pretty terrible stuff on machine tools. Machinery's Handbook specifies the same speeds and feeds and tool rake as steel, so that's what I'm using. Now the trick with this stuff is it deforms or deflects rather a lot under the cutter. So you'll see every time I bring the cutter back, it actually keeps cutting quite a bit. And that's because on the forward stroke of the tool, it was deflecting as much as it was cutting, and then on the back stroke, it's relaxed a little bit, undeflected, and it cuts a bunch more. So you got to account for that. When you're taking your measurements, it's very easy to remove too much by accident because of that. But once I've removed what looks like about the right amount, then I'm going to clean that up a bit with some emery and then a little bit of red Scotch-Brite after that. Again, this is just an aesthetic thing. I'm just trying to thin the flanges out so they look closer to how the original ones did on the brass boiler. I just want to make sure I don't thin anything out too much. That's looking fairly presentable. So now the final step is to true up the end of the flange and bring it to final dimension. On a traditional interior head boiler, this step is somewhat optional because you're not going to see the end of the flange, but of course on this one the flanges are on the outside, so I do want the edges of it to look nice, and the flanges are also much thicker currently than I want them to be. The oil that you saw me put on that tool is actually whey oil. This is a tip I got recently from another model engineer on YouTube. I think it might have been Nigel over at Go Create Hobby Machine Shop. If it wasn't him, this is an excuse to plug his channel anyway. He's doing a 5-inch gauge Lion locomotive build that is absolutely wonderful to watch. He's doing incredible work on it. Go watch that. But anyway, more to the point, I've always used WD-40 as cutting oil for non-ferrous metals. I find it works really well, except on copper. It's never worked great for me on copper. And the person that I learned this trick from said, no, try going hard the other way. Use the thickest, stickiest oil you have. In this case, whey oil. And I gotta say, it works really well. So whey oil is my new go-to cutting oil for copper. This pressure turning setup was working pretty well, but the tool pressure with a grooving tool like this is very high. And I think possibly also some of that cutting oil was getting between the mandrel and the part and starting to slip. And this setup started grabbing and stalling more than it was turning after a while. So I had to switch gears a little bit. I took it apart, cleaned everything up, and added some super glue to my fixturing. That really worked well. I was actually able to take heavier cuts after this, and I never had the part stall on the mandrel after that. For the second head, I did it entirely with the super glue and the pressure pad together. Honestly, the super glue was so strong, the pressure pad might have been optional at this point, but, belt and suspenders and all that. For final dimension on these flanges, I'm trying to go as thin as I'm comfortable doing. It will necessarily be thicker than the original ones because my material is more than twice as thick. So the thickness of the material dictates your minimum flange depth because, of course, the thickness of the material at the end has to be accounted for. So I made it as thin as I could, and more importantly, I made them both match. So it should have a similar look to the original, even though my flanges are going to be a little thicker than the originals. I'm quite pleased with how those came out, though. They're nice fits on that shell. The flanges look nice, and I think the look of the original, the spirit of it, is reasonably well captured there, even though, obviously, as you can see, my flanges are deeper, but I think that's going to be okay. Next up, I'll measure the locations of the holes on the original, because I'm going to need holes for all of the fittings that go in there, of course. The same 3 holes in the same places. I'll do this on the milling machine. I'm holding that as lightly as I think I can get away with without it moving so I don't crush that tube. I'll find the fixed jaw of the vise, and that'll give me the center line of the tube with the radius of it, and then I'll center up on the ends of the tube, and then I can position all my holes from here. There's my whey oil again for cutting. I'm going to start by spotting these 3 holes. This tube is going to need internal support for the drilling though, which will deform it otherwise. So I took the backer from the hammer former and turned it down a little bit so it was a nice close fit inside the tube. And I'll just drill into that as a sacrificial support for the inside. I'm going to do this with step drills. Step drills are really great in thin material. They don't grab like twist drills do, they don't pull upwards like twist drills do, and they make rounder holes than twist drills in thin material. Twist drills tend to make 3-lobed holes in thin material. They actually always make 3-lobed holes, you just only really notice the effect, particularly in thin material. The downside to step drills is they need a lot of depth under the part in order to get down to this diameter on the bit that you need. And with model engineering setups, that's frequently a deal breaker. You often do not have space under the part on these small pieces. But in this case, I do. So I did one end, transferred my sacrificial mandrel thing to the other side, and drilled the same hole. the mandrel kind of self-aligns on the step drill once it gets close. You can kind of eyeball the clearance cut that was made on the first hole, and then push it down to the middle, eyeballing it roughly again under my dimple there. Again, if your hole is anywhere close to the step drill's new location, it will self-align with extreme prejudice once it gets through the material. That setup seemed to work really well. There's definitely an art to working with thin-walled material, thin tubing especially. It can be difficult to fixture or do operations on without distorting or crushing it. But that seems to have gone well. It's certainly looking like a boiler now. Over to the lathe now, I'm going to make some boiler bushings to go in those holes. Boiler bushings are little flanged pieces of bronze that give you more depth in order to put threads into a thin boiler shell, and they also convert the joints of the shell from tension joints into shear joints. Solder is strong in shear but not in tension, so you can't solder things securely to the surface of a thin wall like this. You have to have a vertical surface for that solder to hold on to. Boiler bushings give you that. The factory boiler did have boiler bushings, but they were on the inside. They were like threaded washers, essentially, that had been threaded into the backs of the fittings and then soldered in place after the fact. Again, it's probably well suited to manufacture, but I'm going to do it the traditional model engineer way. It's time now to put the threads in this thing, but figuring out what the thread was supposed to be led me down a bit of a goose chase. They're definitely not M4 and they're definitely not M5. Remember, I determined that the center bushing was definitely M6, probably M6-1, but these smaller bushings on either side seemed to be imperial. The major diameter was 4.8 millimeters, which is not a metric thread. However, they are a pretty perfect fit in 1032, which is of course an imperial thread. Now that seems strange. Why would the center bushing be M6 and the two outer ones be 1032? I was pretty stumped by this. I thought maybe this was something about outsourcing the smaller pieces to some other company, but it was all made in Germany as far as I know, so it should all be metric. I talked this over with my patrons, and one of them gave me, I think, the right answer to this. They are not metric or imperial, they are BA threads. What I thought was M6-1, as you can see, is actually a perfect match for 0BA. And this other one, which is very close to 1032, is actually probably a perfect match for 2BA. You can see the major diameter there is 4.7 millimeters, which is 185 thousandths. The major diameter of 1032 is 190 thousandths. So it's a bit of a loose fit in 1032, but that's what I have. It's a little bit loose. And the thread pitch for 2BA is virtually identical. It comes out to like 31.25 threads per inch, but 32 is close enough. So that's almost certainly what these are. That surprises me because it's German. I didn't know anything German ever used BA threads, but I don't know. Seems like they did. I don't have any way to verify that on hand. I don't have anything. I've never even seen a BA thread here in North America. I've been working on mechanical things my entire life, and I've never seen or heard of anything BA anywhere. So that stuff's just unobtainium here. I could special order online somewhere the fasteners and the taps and dies and stuff, but I mean, we're already here. I've made the M6, I've made the 1032, and they're compatible, so we could just kind of got away with that. And Yahtzee. Quick test fit of all the bushings before we move on. You can see I've measured and marked the actual hole diameters on there. Step drills are nice, but they do tend to cut oversize, and all three of those holes are a little oversized. But that's not a problem in a situation like this. Just drill the holes first and make the bushings to match. And that's definitely looking like a boiler now. So it's time for some silver soldering. Let's get all of the little bits into the pickling acid, get those all cleaned up, and get everything fluxed up. And I'll get some little pieces of solder positioned around. I'm going to do this in 3 stages. First, all 3 bushings at once because they're so close together. I'm not going to be able to do them individually. I'm using my highest heat range silver solder for this so that they won't be damaged by later stages. That was quite easy to do, very quick with the smallest torch I own because these pieces are all so small and so thin. Then clean up and repickle everything. Now I can flux the first of the heads and get this fitted onto the end. I'm going to use a lower heat range of silver solder for this so that I can do it without damaging the bushings. Because these flanges are so thin, there's really nowhere to set little pieces of solder on there. So I'm going to have to do this the harder way, which is to heat the joint until it seems to be hot enough and then touch the solder in there so that it flows. This is much more difficult to do well, requires a lot more skill, and it's easy to blob solder down the sides of the part and all over the place. I'm getting a little better at it. I've done more of this lately, but it's never as easy. I always prefer the little pieces of solder sitting in the joint already. It's much easier to get a nice looking joint that way, but I really didn't have any choice here. So I just very carefully worked my way around, heating up the joint, making sure I've got solder all the way around, and then a final wash to make sure it all flows. A little inspection from the inside, and that's looking pretty good. We won't know till the pressure test, but so far so good. Then the other head was done the same way. Final pickling and cleanup. We can do some visual inspection on those joints. I gotta say, I'm pretty pleased with those. I see nice fillets of solder all the way around every joint. No areas of concern there. But the eyeballs don't mean anything in boiler work. The truth is in the pressure test. So we fill it all the way up with water. This is what we call a hydrostatic test. Do not do this with compressed air. I have to say this every time. Someone always comments, why don't you just put compressed air in it and spray it with soapy water? No, that's how you make a boiler explode and you die. Air is a spring, and when you compress it, it stores energy. And if a boiler seam fails while you filled it with compressed air, it will explode. We do this with water because water doesn't compress. So if a seam fails under pressure, the only thing hurt is your pride and the first 3 rows get wet. I am pleased to say, though, this thing is holding pressure like a champ. There is not a single drip, a single moist spot anywhere on any of these seams. Honestly, my pump is leaking more than this boiler is. And by more, I mean non-zero, because that boiler is not leaking at all. I'm very pleased with that. I think only one other time in my entire life have I had a boiler pass a pressure test on the first attempt, so I am feeling pretty chuffed with myself about that. This thing is a champ. Honestly, it held 60 psi all day. I think it would do 150 psi, honestly. Maybe north of 100 it would need a stay on those flat heads, but this little guy is a pressure champ. Very, very happy with that test. Once again, I used the check valve in the pump to hold pressure during that test, which is why you saw the pressure dropping on every backstroke of the pump. For anything more than about 50 psi, you really need a dedicated check valve for a test like that. Let's see if it looks the part. And there it is in position. I am going to need to modify that sheet metal a little bit to accommodate my thicker flanges, but other than that, it seems like a perfect fit. And the original whistle is going to thread on there. The other fittings were either lost or damaged beyond repair before I got it, so those will be remade, but I think we can salvage the whistle. Now, final finishing is an interesting question. The traditional model engineer thing to do would be to paint it black with high temperature paint, both because that looks prototypical and because it hides all of the silver solder joints. I don't know if I'll do that here. The copper looks nice and the original was unpainted, so that kind of seems spiritually correct. But as nice as the copper looks now, the thing that YouTube never tells you about yellow metals is they tarnish very quickly. Within a week or two, this will be dark brown in color, and in 20 years, it'll be green. I've never found any kind of clear spray or anything that prevents yellow metal tarnishing. If you know of such a product, sell it to every boat owner in the world and you will be rich. So not decided yet on final finishing, but I'm still thinking about it. Thank you so much for watching. Thanks to my patrons for their support making this happen every time, and I'll see you next time.